So today I'm going to present a recent paper of ours. It's on our archive. You see the link there about generative Bayesian modeling with implicit priors. And it's really just a small quality of life improvement if you're doing Bayesian simulation studies. So if I wasn't an academic, I would probably write a blog post about it. But then I also have PhD students who need to write a dissertation and they need papers. So we add some mathematical fluff around it and then call it a paper and submit it somewhere and try to argue that it's relevant. But it's really just a tiny thing which helps us in some cases. Okay, so the problem we are often facing is that the models we are working with are quite complicated, so we cannot understand their properties analytically because the posterior is not analytic. So what we're doing is simulation studies. So in the Bayesian simulation study, you're specifying a model and you're sampling. You're generating data from the prior predictive of that model, and then you are, analyzing that prior predictive model, prior predictive data with said model, for example. And the key challenge, that perhaps a lot of you are familiar with, is how can we convince the prior predictive to generate sensible data? Yeah, so we have specified our prior with some hyperparameters, and then our data that we are getting out of is completely garbage. And then, of course, everything we do based on that garbage data is probably not very convincing. So this is just the key question, and we are presenting a very simple idea to, as a quality of life improvement to get more sensible data out of prior predictive distribution. The relevance would be any kind of Bayesian simulation studies. For example, if you want to do simulation-based calibration on your model and want to check whether your stand implementation is correct and everything is reasonable, but then sometimes, even in simple models, SBC sometimes fails just because the prior predictive produced garbage data which led stand to crash or something. So I'm going to show examples for this. So this is something we want to avoid. We don't want SBC to fail just because we are unable to specify a reasonable prior. So what we are proposing, so to speak, but of course this has been suggested in literature in a lot of places beforehand, is that our prior, we let our prior inform by a little bit of data. And what we see is that we need only very little bit of data to get from a garbage prior predictive to a really good prior predictive that creates quite sensible data. And I somehow managed to sneak in Bayes' theorem about here at the top, but I hide it because I'm not calling it the posterior something. I'm calling is now the preconditioned prior, because I'm adding a tiny bit of preconditioning data that is not actual my real data I want to analyze. It's something different. We can talk about where it comes from in a bit. But in any case, we're just adding a tiny bit of data, and then we're having this preconditioned prior posterior predictive, which is easy to sample from. So we use stand, for example, to sample from this posterior based on the tiny bit of data. We represented this distribution via draws, and then we can of course sample from that posterior predictive as usually, only that we don't call it posterior, but we call it prior. The thing is, of course, our preconditioned prior now based on that bit of data is usually implicit because we can only represent it via draws. We can, try to fit a parametric approximation on that prior, but it becomes awkward if our model is very complicated. We have lots of parameters that are all somehow dependent, and finding a parametric approximation is not so easy. And even if we found it, then shoehorning that back into stand is a lot of effort. For example, Sebastian Weber has done this with the meta-analytic predictive, the map priors, but it doesn't work so generally. So we just settle with having our prior, our new prior, implicitly in the form of draws, and it still everything that we want usually works. So here I'm just going to have a short illustrative example. I'm going to show the details of this example a bit later, but what we are here having in the background is a GLM with 15 predictors, and we have a gamma likelihood with the log link. So let's first focus on the first column. We don't have any preconditioning data, just our prior. These are weakly informative priors. For example, here we see two coefficients, beta 11, beta 14, and they both have a weakly informative normal 0, 1 prior on them. And then all the other parameters have some semi-reasonable weakly informative priors. Yet if we compare our observed data, this is a real data set behind it, the body fat data, compared to what the prior predictive produces, on the x-axis we see what the original response looks like between, 5 and 50 or something. and then, you know, what the prior predictive produces is like 10 to the power of 6. And this is not a bad prior. This is like a reasonable weakly informative priors, and we are off by 6 orders of magnitude. If we were less careful with our prior, we would be off by 200 orders of magnitude. But even, like, I think there's an example in this visualization in the Bayesian workflow book where we can easily get more counts than the mass of the black hole in the middle of our galaxy in Poisson model. So this is basically the same thing. In everything that has some kind of nonlinear transformation, specifying priors that produce reasonable prior predictive data is hard. We also can look at the, you know, prior R square, how much variance is explained. It's like almost 100% explained variance. It's not a sensible prior, but it's also hard to specify a prior that would produce something more sensible. Conversely, if we just add a tiny bit of data, like 5 observations or 10 or 20 observations, which is not much, we have like, I don't know, 16 parameters in the model. We're just like adding a tiny bit more data than we have parameters in our model for the 20. You know, the prior shrinks a tiny bit. We are actually including even some correlational information. And suddenly, even after 20 data points, we are already at the right order of magnitude. So what we see here, like illustrated, is that just a tiny bit of data helps us to get in the right order of magnitude without having to tune our hyperparameters of the prior like endlessly or like accidentally making it more informative than we want in some weird direction that we don't understand. We're adding a tiny bit of data to nudge it in the right direction, and also R square suddenly looks much more reasonable. Still a bit big. Okay, so I promised you some mathematical fluff. So it's, you know, of course, you know, we can look at now how does the posterior look like for some for these kind of preconditioned priors. So suppose we are conditioned on both the preconditioned data set and our actual data set that we want to do inference on. So we have the posterior based on, I actually didn't say this, but the alpha, our prior hyperparameters, yc is the preconditioning and y is the actual data. So if we want to have the prior, the posterior based on our preconditioning prior, all we have to do is basically we have our original prior, then we have the likelihood from our preconditioning data, we have the likelihood from the actual data. Yeah? So we never need to like represent explicitly this preconditioning prior. We just, you know, add a tiny bit computational requirement by having a tiny bit more data in our STAN model. And since usually we think that our preconditioning data to be small relative to the data we want to analyze, it shouldn't add too much, you know, computational overhead. But we still can get the, you know, exact posterior in the way we want, or like asymptotically unbiased via MCMC. Okay. Of course, the issue now is when we're doing a simulation study, people can rightly argue that now all the results we're having are, you know, conditioned on that one preconditioning data we choose to use. And so any kind of artifact that may be in that tiny bit of data will propagate, of course, to all of our simulation results. So then we can add more, you know, integrals around it, which always looks fancy. We never evaluate them, right? But like they look nice. So we can say, okay, look, our preconditioning data comes from a distribution of such data sets. For example, if we have like our like some real data set, then we can bootstrap from that and like take tiny bit of data sets and do this repeatedly. And then like for each of these tiny data sets, we're computing our preconditioning prior. And then we can integrate over it, like build a mixture of all of these individual priors to get like a prior predictive where each individual preconditioning data set creates like a reasonable prior, and when we have a mixture of them, they're still reasonable. Yeah? It's still easy to sample from that. We are first sampling, you know, a new tiny data set, and then we're sampling from the corresponding preconditioning prior posterior. So, you know, this way we can basically avoid being too much like focused on a single data set, but of course we can like generate many of these tiny data sets that help our prior predictive to look reasonable. So where does this kind of preconditioning data comes from? You know, there's lots of literature, as I said, in different ways where they are, you know, that suggest adding a tiny bit of data to your prior. For example, the kind of whole field of historical data priors, or like power priors that suggest to use historical data. We can do this here too. Or you could use your current data, which you seek to analyze if you're careful. I'm saying if you're careful because don't, you know, double dip into your data by first using as a prior and then using the same data set again. But if you just want to have a simulation study to study the properties of your model, of course you can use your current data, nudge your prior in a little bit of the direction of your real data, thus making the prior more realistic. As long as you're not using the preconditioning prior and the inference in the end, you're fine. Or you can even simulate data from that model, but given a sensible fixed parameter configuration. So even for complicated models, it's often easy enough to find a fixed parameter value or configuration that generates reasonable data, but it's hard to have this whole sensible prior around it. But if we can find a sensible fixed parameter point, we can simulate data sets from that. We understand what these points usually mean, and then we have our preconditioning data available from simulations without actually ever having to sample from the original prior predictive. Okay. So I want to showcase this on the basis of simulation-based calibration. I assume a lot of you are familiar with it. In case you don't, here's a quick rundown of what simulation-based calibration looks like. So we're using SBC to verify Bayesian models, Bayesian inference algorithms, checking the trinity of our sampling, our generative model, our model implementation, and the algorithms that are estimating it, for example, MCMC algorithms of Stan. So what we're going to do is we are choosing how many of these data sets we're going to generate. Then we are first sampling from the prior. Then based on these prior samples, we are sampling from the likelihood. So in essence, we are sampling from the prior predictive. Then we are obtaining draws from our posterior distribution using, say, Stan. And then we are computing the ranks of any kind of quantity that we're interested in, let's say a specific parameter itself, computing the rank of where that prior sample that we have drawn is within the set of the posterior draws of that corresponding quantity. And if everything is correct, our implementation is correct, our sampling fits, and everything is nice, then this distribution of ranks will be uniform. That's the underlying idea of SBC. And we can extend this also to these, implicit priors with preconditioning. We would first choose a number of preconditioning data sets, then how many of SBC data sets we want to generate for each of those preconditioning data. We are, then sampling draws from the preconditioning prior, then, corresponding data from the likelihood, computing the overall posterior where we precondition both on the the preconditioning data and then the new simulated data, and again computing the ranks, and if everything is fine, then things will be uniformly distributed. So this SBC still works like this, we just need to adjust it a tiny bit. So what I now want to kind of illustrate is how bad SBC can actually fail if we are using still reasonable but weakly informative priors, and how easy it is to fix with preconditioning. So in the first case study, we are predicting the body fit percentage from some simple body measurement like height and weight and size of the neck or something. And here we're using a gamma GLM with 13 predictors and some reasonable weakly informative priors on the parameters, where alpha is a shape parameter and mu is the mean which we are predicting on the log scale. So when we run it like this, or with similar priors, without a lower censoring or truncation bound, the numerical underflow to zero prevents the model from fitting at all to the prior predictive data. That is, we are generating observations that are so small, so close to zero, that R or Stan round them down to zero, and that the gamma likelihood fails on initializing at all. And it's nearly impossible to generate data sets which don't have these underflows. So we don't really know what to do. We would have to specify much more narrow priors, but it's not always easy to do so. So what happens with SBC? If let's say we're employing censoring, so we say every observation that is below 10 to the power of minus 16, so double precision, relatively small, we are censoring down to 10 to the power of minus 16. That shouldn't make much of a difference, right? It's so small numbers. But what we see is with the original prior, we would like our black lines to be within that blue curve, but it definitely isn't. So SBC fails completely with the original prior, where we are using a truncation bound or censoring bound of 10 to the power of minus 16. We can also do it with the smallest non-zero value we can represent in R, which is 10 to the power of minus 323. Still it fails for some parameters to be calibrated. And if we're just like adding 15 preconditioning observations and doing the same thing for the implicit prior, everything works fine, right? That's an easy model. Stan knows how to do it, but because our prior predictive data is so garbage, we are running into like numerical or any kinds of issues like this. Then we have a second case study where we're having a really complicated distributional structural equation model where we have 4 latent variables. It's like actually from a paper of ours where we run into these problems. We're having 4 latent variables, and each of them, like, we're predicting their mean and their standard deviation. So it's like really messy, and we had a really, really hard time finding like sensible priors to generate sensible data from that, where SBC didn't fail, and now with this new approach, it's actually quite easy. So when we look at we have very narrow original priors, and SBC, it's in the first column, like fails really badly. And if we just add a little bit of data, like 6 observations or 10, which is like not even the number of parameters, we immediately see how calibration, works well. So we're not cheating, we're just like nudging the prior predictive in a direction where we getting more sensible data that also Stan and other probabilistic programming languages could better work with. And also we are decreasing the amount of sampling issues like low R hat, etc. Okay, so to summarize, so preconditioning the prior on a little bit of data greatly helps with any kind of prior predictive simulations. In particular, we can prevent SBC from failing due to priors implying like very extreme data. The computational overhead is like relatively small because we have just like small preconditioning data. And I want to thank Luna and Max for all their work. Our preprint is available. I will put the slides online, I think, also on the Stan website and also on my own website. So you can also check out my lab's website for all the preprints and talks and references. Thank you. Yes?
Did you try different combinations of like 5 or 10 observations to see how much it would vary?
Oh yes, before I'm getting like plugged off, here you see 0, like SBC. This is like a SBC test statistic. This is well calibrated. No preconditioning data, original prior, everything is completely dead, and we are adding 6. I just skipped some here. We already see it's going to be well calibrated for some parameters, and as we increase this further to 10, it gets well calibrated. But I'm not sure this was your question.
I guess how big is you took 6 observations from how big of a sample size?
It doesn't really matter. In this case, we just we simulated tiny, like a small data set from a fixed parameter vector. Okay. So it doesn't really matter from which set we are doing this. But of course, if we were checking, we didn't want to condition on like a single small data set. Yeah? But I should say that basically, usually what works well is that we have roughly the number of parameters. This is like not quite clear what the number of parameters is in terms of preconditioning data, like where barely our fragmentist estimator is would be identified. It's usually sufficient to fix things. And now I'm giving up my cable. Yes.
If I primarily care about the posterior, is that still useful? Like the models you showed, right? Like the problem goes away as soon as you add data.
Yeah.
So it is just the priors that are sort of problematic. So.
Yeah. So it's if you just care about your posterior, I mean, there's like decades of research who don't talk to each other, but there are different streams of research who suggest to like add some data to your prior. And it's usually like for base factors or for like posterior inference. So what basically the new thing we add here is basically just like focusing on the generative modeling of the simulation study perspective of this. So yes, you could use it for your real data, but then you would have to, of course, take care of that you don't double dip into the same data. Yeah.
So the gamma, right? It is correlated, like the parameters are correlated to each
Yeah.
other. Do you know if you did a different parameterization, like in the sense of when things fail, is it often because of this correlation between parameters? Is it because of numerical issues? Do you have any sense?
So in the first case, it definitely fails due to numerical issues, which is the numerical underflow to 0. it's a kind of a, in this case, it's a toy example. We could fix our original priors to make it work. The second example, in this latent variable model, the issue is basically since the latent variables also affect the standard deviations, you know, you have like a latent variables between 0 and 10, everything is fine, and suddenly it's 10 million. And it's very hard to prevent. And then, you know, the model is, I don't know, 2 different scales of the parameters. And I'm not entirely sure what fails there. It's just probably highly complicated posterior geometry that gets really awkward with very awkward data. My best guess. But I've seen this kind of problem a lot where on real data things work out and on simulated data things fail terribly. I think that's the fix for that.
Okay, we take other questions.
Good, okay, thank you.